Okay, hi, I'm Caleb,
I'm Ian.
and we're here to show you our project, which turned out to be bigger than expected. So, we designed a dual slope analog to digital converter, before we begin going through the full system, we'll show you how what the basics are. So, our design goals were to design an analog to digital converter capable of converting audio frequencies, at least 10 kilohertz, is how we define that, with a plus or minus 12 volt bipolar input range. And we wanted the design to be reasonably low noise and have an 8-bit resolution. And this is going to be done with discrete logic components, so like 74 series logic and op amps and comparators and passive components. So the basic principle, that's
Okay.
yours.
So this shows the black diagram of the dual slope, and it shows that there's the integrator. The integrator generates two different ramps, one with the input voltage and
For a fixed amount of time.
and another one with the reference voltage. So the binary counter is initially reset to 0000.
Well, yeah,
Is
in
it?
our case.
In our case,
So basically, there's a fixed timer.
Okay.
Yep. So you have a fixed length timer. At the beginning of the conversion process, that timer is 0 and it counts up, so you're integrating for an amount of time. And when that timer is done, this input of the integrator here switches to a reference voltage of the opposite polarity. You want to continue, Ian?
I was just explain that the analog input voltage is integrated by the inverting integrator and generates a negative ramp output.
Yep.
Then the
And-
output of
yeah.
comparator is positive, and the clock passed through the AND gate, which shows over there.
Well, yeah, our design doesn't actually have that, but
Oh,
this is a
just-
general
yeah.
block diagram. So basically, the end of it, the rest of the conversion process, this counter is counting for until the comparator returns to 0. So here's a graph of it. Basically, we have the timer running here. At this point, we switch to the reference, that's the opposite polarity, and the integrator discharges its capacitor. When this crosses 0, the count on the counter, which is separate from the timer, ends. So basically, well, yeah, that's pretty much it, actually. So it's a little bit more complicated than a single slope design, but not a lot. So our design, we're going to discuss a few different operating modes. So there's sleep mode, which means that the integrator input is grounded, the comparator output is ignored, so basically the comparator could be a little bit noisy, and the noise won't affect any of the other rest of the circuit. And the all flip-flops and the timer are cleared, as is the counter, but the output register from the previous conversion is still high, or still what it was at the end of the conversion. And then there's charging mode, which is where we integrate the input voltage, and then it persists until the timer hits its max point, and the sign of the input voltage is determined in the case of ours, since it's bipolar, and used to choose either a positive or negative reference voltage. And then the discharging phase directly follows that, and that's where we are integrating the positive or negative reference. If the input is positive, then we use the negative reference and vice versa. And the counter is enabled, and it stops when the comparator switches its output. So yeah, that's the basics of it. So now we're going to, there we go.
Going to
Yep, we're going to transition over to, let's see, never mind that, that's the wrong thing. We're going to transition over to some of the analog design elements of this circuit. So we're starting with power on reset, right?
Yes.
Okay.
For the power on reset,
You should explain what it is first, maybe. So.
yes, power on reset, this senses the input voltage that measures the digital voltage. And in case the digital voltage is too low, it resets the digital system, and one of the power rail is disconnected, or the user send the reset system.
Yep. So, yeah, basically there's this input here that detects whether the user asserted reset or whether the one of the analog supply jacks is disconnected, and it will reset the digital circuit. It's mainly a precaution, especially for initial turn on when we don't necessarily know the states of flip-flops and such. So you can see here, these are the power jacks, and there's some decoupling around it. But these here are switches inside the power jacks that are often used to switch between battery and between a battery and supply, but in our case we're using them to switch the digital circuit on and off, essentially. Well, not on and off, but enabled and disabled.
So this one shows the digital over voltage protection. For this circuit, once the voltage across divider reaches the diode voltage, the comparator turns off. And since the transistor has a built-in diode, if the input voltage...
We'll demo that in a sec.
Yeah.
So,
If the input voltage is negative, therefore there's no voltage protection.
Yeah.
We thought about putting a diode in the circuit, but since the CMOS circuit draws a little current, we were concerned due to the nature of the load, the diode will cause an unwanted reset.
yeah, so basically, if there's no current flowing through the diode, it will go into cutoff and turn off the voltage, which could cause the power on, turn off the digital voltage, which could cause the power on reset to activate when we didn't actually want it to. It is worth noting also that we just added this because we were going to use the same type of power jack for the analog and digital power, and digital chips do not like 15-volt supplies in general. So we do have a simulation of this though, and that is not it. Here's the simulation. So basically, I'll just run it. It's the same circuit essentially. So what we've got here, you can talk about it, Ian. Or, that's what that's kind of what she already talked about.
Okay.
So it's just basically a MOSFET that turns off in the case that there's more than 6 volts at the digital supply rail. One thing about it though, like she mentioned, is that it does not work for negative voltages. That needs a little bit of revision because that could also be an issue. I think that's pretty much it for this. So that's just a simple simulation. It's showing the input voltage on the x-axis versus the output voltage on the y. Yep. And now let's move to the the analog reference.
Yes.
Okay. So that is right here. So
for analog reference, this these here are the shunt regulators, and they required a lower current than Zener, and they're less linear and has much sharper
Yeah.
voltage.
So yeah.
It also uses negative feedback due to potential noise.
Yeah. So yeah. Actually, I can show you the data sheet for the part that we chose. It's hold on. Let's see. Yeah. So we chose the TL431. And you can actually look here. So with a Zener, you'd typically have a much shallower knee here. So it would be something more like that. In this case, this thing is very sharp and handles supply rate changes very well. So yeah, basically it's basically a very stable Zener. Let's see here. So going back to this, yep. Okay, so the reference, like we described earlier, just is for part of the conversion process. So do we want to discuss this now?
Is this the...
This is the integrator. Here, this part
Integrator.
is. Yep. Do you want me to, or do you want to?
Oh, yeah.
Yep. So
So I was thinking about the other one, but this integrator, if the integrator input is high, the comparator is high.
yep.
The
Well,
yeah, it charges, and this runs for 8 microseconds according to
Yeah.
the simulation that we did,
Yep.
and then it switched with reference voltage.
Yep.
The,
So
yeah.
basically, yep. What we did here, we have a buffered integrator because this here, the switch IC that we used, is has like 100 ohm resistance. So first we buffer the integrator, and then here's the integrator itself. We also added some switch across. The switch IC has 2 switches in it that operate simultaneously. So we also are able to make sure this capacitor is discharged by putting at the most 100 ohms across these terminals. It'll probably be less than that, but basically it will help to speed up resets. Here's the comparator. It's an open collector design. Okay. And yes, we did simulate this as well. So what we have here, the switch we couldn't simulate because it's a mixed signal IC, but we do have this supply here using PWL data. Oh, wait a minute. It's well, it's quite long actually, but it oh no, it isn't. It basically simulates the digital portion of the circuit. And we also simulated this with noise. So if we take a look here, here's our input voltage. Worst case input voltage is 12 volts. The timer will run for 8 microseconds, which we found is a nice balance between speed and linearity, because since there's a fall time here, this curve shows up. We also simulated it, like I said, with noise. So here's 0 volts, then we switch to the reference. The integrator is inverting, which is something worth noting, that when there is a negative input voltage, the output, the sign bit at the output is going to be high, which means that if there's a negative input voltage, this slope will actually go this way, and we'll use the positive reference, which will cause it to go back down. But anyways, one more thing to show here is the output of the comparator. Now, there's a lot of noise here, and we experimented some with using hysteresis in the simulation, but we've designed the digital circuit in such a way that this noise here is actually not a problem, because the output of the comparator is only measured at this point here and at the end here, or, well, actually during this full discharge cycle here, meaning that noise from that is very unlikely. well, encountering noise problems from that is very unlikely, since our input is nowhere close. And the integrator does a pretty good job of filtering by itself, since an integrator is basically a low-pass filter. Let's see here. That's it for the integrator. So
yeah, you might mention that the integrator voltage crosses 0, it switches again.
yep, the
according to
comparator switches
yeah.
right there. Yep.
Okay.
Let's see here. Okay, next we're going to discuss the priority encoder, which this is a small logic section. Oh, here it is. The priority encoder is just a small little area of logic. Its only purpose is to take 4 switch states, essentially. So these are not inputs from the switch, they're inputs from our digital circuit, but each one corresponds to a switch state. So what we have here, like this A, if it's high, it will be tied to ground at the switch. That means that any of the inputs after it will be
They override it.
they won't override that. So during the conversion process, though, while the timer's on, we'll have B, which will, these go to the switch itself. They control which mode the switch is in. And again, these can be anything, and they don't affect it. Once that's done, it will choose one of these. So depending on the situation, in the final digital circuit, these will actually be complements of each other, but so they're set at the lowest priority. Other than that, that's a fairly simple circuit. This here is a inverter. It's just wired as an inverter. It's a NOR gate that with its inputs tied together. And then the rest is just some combinatorial logic to actually get that done. You might wonder why we chose NOR gates, and the reason is actually a practical reason. It's that NOR gates were cheap, essentially. We could easily get a package with 3 NOR gates in it, and so that's what we used. Let's see here. Oh, yes. And now we're going to the main logic. So this is an early simulation of it here. And how this works, the address is the output of the priority encoder, and that's controlling the switch, which, as I mentioned before, if I were to go here, it's controlling which of these it's going to use. So either this analog ground, input voltage, or the references. So those 2 bits there control that. So going back to here, though, for now, we've got basically a trigger line here. That's this trig that turns on the conversion. It starts the conversion process. There is a clock divider in the timer. That was just to get the right timing. The final design runs at 4 megahertz, and so this is a divide by 32 counter that we're using as a timer. So if I were to start this simulation and trigger it, so I've now asserted the trigger, this flip-flop here locks the trigger on, and now you can see right here that this is counting up. Once it gets to the end, I'm going to stop it just before it gets there. Let's see, waiting. Yep. Okay, that's pretty much at the end. So what's going to happen is this RCO output of the counter here, it's a 74HC161, will go high. that output will tell it to sample the comparator, which in the case of a positive input, that comparator will be low because the op amp, the inverting integrator is goes down when the input voltage is positive. That being low will cause this multiplexer here to switch to invert mode. So basically, this multiplexer just selects between inverting the comparator or not inverting it. And then we will, so if I run this clock a little bit, you'll see that there. So this clocked this this flip-flop on. It also set the data input of this flip-flop high. This flip-flop is not too concerning at the moment. It's just used for resetting the whole system. It was necessary in order to make sure that the system would not reset in any other, well, yeah, it was basically just used to reset the system. So it's not, we're not too concerned about it. You'll see now that though that this address changed. In the dormant state, it was 00 for ground, and in this, and then it was in the VN state, which was because the output here of this RCO is inverted, so this one was high and this was low, which would be an address of 01. Now it's the address 11, which changes to, it changes the input of the integrator to the negative reference. So now, if we let this clock for a little bit longer here, we can see that this is waiting, essentially, this is an enable line on this here. This is waiting for the comparator to change. Now when I switch the comparator high, you can see that that's the count there. The clock will stop. So I'm going to actually manually stop the clock now. And that comparator is now high, which caused several things to happen at the same time. So first, it's disabled this clock. Second, it wrote the or not clock, it disabled the counter. Second, it wrote the count to the output register. And third, let's see, yeah, third, it clocked the sign register, which is just another flip-flop. And finally, it clocked this, which caused everything else to reset. So the this and this to reset, which in turn causes the address to go back. And the conversion process isn't completely done, actually, because the reset line hasn't fully asserted. It'll take another clock pulse to do that. So let's see here. Oh. Did I leave trigger on? Maybe I left the trigger on. Or maybe the simulation is slightly messed up. Anyways, this would normally reset. It appears that I have something connected wrong on this particular simulation. I am going to show one more thing on it. With this comparator high, that means that the input voltage is negative, and we're counting here. I'm going to go through this a lot faster. So that count is happening. Right now the address is set at our input voltage. And okay, that's done. So now this flip-flop here stored that sign, which we use that to make sure that the multiplexer doesn't change due to noise. And now we can go with this comparator, and I can switch it again, and it resets everything. There, it worked correctly that time. I think I may have gone too far or something. I'm not sure why that didn't reset the last time, but this time you can see that it did reset, and we have a binary value corresponding to that amount of time that the integrator took to discharge, and we have the sign bit high for negative. So that's it for that simulation. I will show you, because it's slightly different, our actual design. Oh, there's somebody wanting to come in, apparently. Can you check that, Ian?
Yeah.
Thanks. So we have here our oscillator circuit, which is just it's a 74 LVC 1GX04. Let's see. So we have, this is a ceramic resonator here, and this resistor is used for gain. And this just is basically takes the resonator oscillations in and outputs a CMOS logic level clock signal. And now here we'll take a look at the priority encoder, or not priority encoder, but the main logic. So what we've got here, this is 2 flip-flops, this package is. We have the clock divider and the trigger lock. So the trigger lock is, in this case, it's this one here. So it was moved. And so that goes into the priority encoder. When the trigger is locked, this input stays low, which is the one that overrides the others and would make the input grounded. Let's see, and then we have the, this is, like I said, the other flip-flop in this package is the clock divider. So it just drives this counter directly. It's a divide by 32 counter, which is what we needed in order to get 8 microseconds from 4 megahertz, from a 4 megahertz clock. So basically, when this counter's done, it's been 8 microseconds. Here's the RCO, which causes this flip-flop here, which does the sign checking and automatic reset. So it clocks the sign check, and yeah, and it also puts the input voltage mode, turns the input voltage mode off. And then we have, here's the comparator's output here that goes into our, it's just a single 2 in 1 out mux. It's actually got a complementary output, so, but it's basically the same thing. And the OR gate and our output register, which is the 74HC590. And here's the sign bit flip-flop. One thing worth noting here is this AND gate, which was not in the original circuit. This was added to allow the power on reset circuit to reset everything at any point in time. So that just goes to the clear line there, and it goes to this clear, the clear for the trigger lock. Clearing that trigger lock causes this to clear, so there wasn't really a need to add a second clear line there. And yeah, that's pretty much it. So, there's actually another part that we're going to show you. So the design is essentially complete. The part that is not complete is the PCB design. So do you want to talk about this some, Ian? How about you talk about this?
No.
Nope. Okay. So it's a little bit rough yet, but basically we're trying to be very careful. So most of this stuff here is decoupling. We're trying to be very careful and isolate the ground and analog and digital grounds, and we'll connect them at one point. That will help minimize noise. The bottom will be mostly a ground plane. So right now you're just seeing like some different supply rails and such, where we've mostly avoided putting signal rails on the bottom. And so what we've got here is we've got analog input power jacks, we have the digital power jack, the protection circuit is here with, this is an this here is an IRF 510, which is just a standard power transistor. We have also these, this here, these 5 gates, and then are part of the priority encoder, and this chip contains the rest of it, the NOR gates. This is our switch IC, it's the DG409DJ, and this here is the op-amp integrator and buffer. It's a 2 op-amp package. It's the TL052, which we chose for because it has a fairly low offset, but also because is moderately fast, which means that it can handle the rapidly changing switch input. Which, if we had used a slower precision op-amp, that would have been a problem, because the curve from that integrator simulation, where'd it go? There. So this curve right down here would have been much larger. So we chose a fairly fast op-amp that compromises speed for a little bit of precision. Whoops. Let's see here. And here's the comparator. So then the rest that needs to be done, we need to place the power on reset circuit, this oscillator. Then we need to finish routing the main logic, which is actually fairly small on the PCB because several chips have multiple parts in them. And then this design should be complete, and it should be buildable and testable. So that's it. Thank you for watching. Sorry if this went a bit over time. We will see you at some point. Goodbye.